Welcome to this review of Module 3 of the Derivatives Masterclass. This module was on volatility and volatility markets. When you prepare for the test, you should focus on two main themes. Namely, first, of course, what is volatility? You need to understand what realized volatility is, implied volatility, what is a volatility smile, why is there a volatility smile, what is the volatility surface, etc. And then you need to know how to trade volatility. Trading volatility comes in two aspects. So you can either harvest or trade the realized volatility, and this is typically referred to as gamma scalping. And then you can have a view on implied volatility. That means you have a view how the volatility smile or the volatility surface is changing, and you want to harvest this view. This is typically done with products like straddle, risk reversals, butterflies, calendar spreads, etc. But we will now review this point by point. So then, what is volatility? From a technical point of view, volatility is defined as a standard deviation of returns. Standard deviation, typical move. So volatility describes how an underlying typically moves over a period. Volatility is in most cases expressed as an annualized number. So if I say that the 2-month volatility of an underlying is 20%, this 20% describes a 2-month period, but it is expressed as an annualized number. To understand what this annualized number means for a different period, we need to be able to scale this annualized standard deviation into a typical move over a day, over a week, or over a month. We have seen that standard deviation scales with the square root of time. Hence, for example, if I want to know what is a typical move per day, then I have to take the annualized standard deviation and divide this number by 16. Why by 16? Because a year has about 256 trading days, and the square root of 256 is 16. So going back to the example with having a 2-month volatility which is 20%, that means over these 2 months, the typical move per day was 20% divided by 16, which is 1.25%. But this is probably no news for you. Volatility is a word with many meanings. The most important differentiation is between realized volatility and implied volatility. Realized volatility describes how much the underlying fluctuates over a certain period. It is a characteristic of the underlying over that period. Implied volatility describes how much volatility has been priced into an option contract. It is a characteristic of the option at the point of pricing. You can think of implied volatility as the market's expectation how much the underlying will fluctuate over the lifetime of the option. So in that sense, implied volatility is more forward-looking and realized volatility is more backward-looking. But of course, you can talk about past implied volatility, which would describe how much volatility has been priced into an option at a specific point in the past. And you can talk about future realized volatility, which describes how much the underlying will fluctuate over a future period. Of course, we will only know the future realized volatility at the end of that period. Important to know that there is a trading strategy to harvest future realized volatility. That means the profit of this trading strategy will depend on how much the underlying fluctuates between now and expiry. This trading strategy is called gamma scalping. Here an example. Assume that a trader trades a vanilla option at a 24% volatility. After the trade, the risk system describes the position as having a delta of -50% and a gamma of 4%. My first question: What option did actually the trader buy or sell? Now in this case, this is quite simple. We see that the gamma is positive and we know that the vanilla option has a positive gamma, so this must be a long position in the underlying. Since the delta is negative, this must be a put. So the trader has bought a put. In order to understand how much profit the trader makes from this spot move of up $3 and down $3, let's watch the trader more carefully. When the trader bought the put had a delta of minus 50%. So the trader initially hedged his put position by buying 50% of the underlying. After that, the net delta of his position was 0. Then spot moved by $3. Let's assume first that spot moved up by $3 from 100 to 103. This spot move made the delta of the put changed. Gamma describes how much delta changes when spot moves. Since the spot move was plus $3 and gamma of our position is 4%, the delta of the put changed by 12%. So before the move, the delta of the put was minus 50%, and after the move, the delta of the put was minus 38%. Now the trader has to re-hedge his position. Since he originally hedged with 50% of the underlying by buying 50% of the underlying, he now has to sell 0.12 shares. Then the next day, spot moves back to 100. And with that, the delta of the put is again minus 50%. Now the trader is underhedged. The delta of his put is minus 50%, but net he had only bought 38% of the underlying. So to re-hedge, the trader now buys back the 0.12 shares he just sold yesterday. Over this move, he sold 0.12 shares at 103, and now he buys back the 1.2 shares at 100. This gives him a profit of 12% times $3, which is 36 cents. So over 2 days, the trader has a profit of 36 cents. That means per day a profit of 18 cents. Or in other words, a $3 move resulted in a gamma profit of 18 cents. You can do exactly the same calculation assuming that the move was down up instead of up down, and you get exactly the same result. Namely, that a $3 move results in a gamma gain of 18 cents. There is, of course, also a formula for this. The profit from gamma due to a spot move of ds is just a half gamma times ds squared. If we fill in these numbers in our case, gamma 4%, the spot move is 3, so a spot move of 3 under a gamma of 4% results in a gain of 18 cents. But it turns out that the trader cannot capture the entire 18 cents gamma benefit. While he benefits from being long gamma because he's long an option position, this option position decays in value every day. So we have a theta cost every day. His net profit will therefore be the profit from being long gamma minus the daily option decay. We can estimate this daily option decay by assuming that the underlying moves on the implied volatility of 24%. Because if the underlying moves as described by the implied volatility, then the benefit from being long gamma would be offset by the theta decay. So let's do this quickly. If spot moved as described by the 24% implied volatility, that would imply a move of 1.5% per day. In our case, this is $1.5 per day, and the benefit from being long gamma would then be a half gamma times ds square, which is a half times 4% times 1.5 square, which is 4.5 cents. So the trader's net gain per day would therefore be the 18 cents he harvests due to being long gamma minus the 4.5 cents theta decay, which gives a net daily profit of 13.5 cents per day, or over 2 days, a profit of 27 cents. But the more typical way to estimate your daily option decay would be to just ask your option model. I have tried to do this here, so I recreated a situation similar to the one we described. We have a put option, the underlying trades at 100, the implied volatility is 24%. Now I fiddled with the other inputs so that I get a delta of about minus 50% and a gamma of 4%. Now these inputs imply a theta of $11.61 per year. If I now calculate the expected daily benefit from gamma, I use the formula, a half gamma times ts square. I use the rule of 16, so the typical daily move, assuming a volatility of 24%, would be 1.5%. And if I calculate my gamma benefit, I get 4.5 cents. If I, on the other hand, calculate my decay, my daily decay, I take the 11.61 and divide by the number of days within a year. Since I used here the rule of 16, this rule of 16 implies that we have 256 trading days, so I assumed that a year has 256 days, and if I do that, you can see I get again the 4.5 cents daily decay we calculated before. So the gamma benefit equals the theta cost. At this point, a note for experts. My example was a little bit simplified in that the carry rate was 0. So that means it costs me nothing to carry the underlying, and that also implies it costs me nothing to carry the delta hedge. If the carry rate is non-zero and the underlying moves as explained by the implied volatility, then in an ideal setting, the gamma benefit should equal the option decay plus how much it costs me to carry the delta hedge. To summarize, our trader started with a long put position. He initially delta hedged the put position and continuously rehedged the option to stay delta neutral. This resulted in a pure volatility position. While the trader was maintaining this continuously rehedged delta neutral option position, he was harvesting the realized volatility. If this realized volatility turns out to be higher than the implied volatility, the trade ends with a profit. If this actual volatility is lower than the implied volatility, then the trade ends with a loss. So in that way, option can be used to harvest the realized volatility of an underlying. If you are long vanilla options, you have a positive gamma, and that means you are long realized volatility. On the other hand, if you are short vanilla options, you have a negative gamma, and that means you are short realized volatility. You harvest your long or short position in realized volatility by continuously delta hedging the option. The next topic we should review is the market structure of implied volatility. The volatility skew or volatility smile describes the market prices of options on the same underlying and with the same expiry. For example, the current market prices of 3-month options on a given equity index. The x-axis specifies the option strike and the y-axis shows the market price of the option represented by its implied Black-Scholes volatility. It turns out that in most market situations, options on the same underlying and the same expiry trade on a different implied volatility. In our example, options with low strike prices trade at a higher implied volatility than options with high strike prices. But please note that put-call parity still holds, and hence calls and puts with the same strike must trade on the same implied Black-Scholes volatility. Otherwise, there is an arbitrage opportunity. If in our example the 3-month 1100 strike call trades at a 16% implied volatility, then the 3-month 1100 strike put should also trade at a 16% implied volatility. Otherwise, you can arbitrage the two prices. The main characteristics of a volatility smile or skew are, first, the general level of implied volatility, typically given by the implied volatility of the at-the-money forward options, the tilt of the volatility curve, typically referred to as skew, and the curvature of the graph, typically referred to as smile or kurtosis. In our example, we have a pronounced put skew. That means out-of-the-money puts trade at a higher implied volatility than out-of-the-money calls. A put skew where out-of-the-money puts trade at higher implied volatilities than out-of-the-money calls can be interpreted as the market's view that a down move in the underlying market is more alarming than an upside move. That the market will get more nervous on down moves, but relaxes on up moves. And thus volatility is likely to increase when the underlying market moves down and decrease when the underlying moves up. Equity index options typically show a pronounced skew. A pure volatility smile, though, where out-of-the-money calls and out-of-the-money puts trade at higher implied volatilities than at-the-money options, can be interpreted as the market's view that any move in the underlying is likely to increase the level of volatility. Option markets in foreign exchange often show a pronounced volatility smile. Apart from a strike structure of implied volatility as explained by the volatility skew and smile, there is also a volatility term structure in the option market. That is, the general level of volatility also depends on the time to expiry. In our example, the implied at-the-money forward volatility of short-term options is much lower than the implied at-the-money forward volatility of longer-term options. If we now combine the strike structures for different expiries, we get a surface, the so-called volatility surface. The volatility surface, finally, is a way to summarize all option prices on a given underlying. The volatility surface is a snapshot in time of the option market on this underlying. Trading implied volatility finally means expressing a view how the volatility market, that means the volatility skew and the term structure, will change over time. Here an example. The red line in the graph on the right shows the current volatility skew. You expect the skew to change. Your view is that the skew will change as described by the gray lines. The question now is, what is your trade to harvest your view? Now it seems that your view is that the general level of volatility is going to go up. but you have no view whether the skew will increase or decrease, or whether the kurtosis will increase or decrease. Trading the pure general level of implied volatility is best done by trading at-the-money options. Since your view is that the general level of volatility is going to go up, you will buy at-the-money options. But by buying at-the-money options, you pick up some deltas. Since you have no view on the direction of the underlying, you only have a view on the level of implied volatility, you delta hedge your option by selling half of the underlying. Let's briefly summarize the typical trades to harvest a view on implied volatility. Say we start with a flat volatility structure. No skew, no smile. We have the strike prices on the x-axis and the implied Black-Scholes volatility on the y-axis. The volatility is the same, say 20%, for all strikes. If your view is that the general level of volatility increases, you want to be long Vega, and the purest way to express this is to buy at-the-money options, typically at-the-money straddles. If your view is that the market will change and we will see a pure put skew, then you buy low strike options and you sell high strike options. The typical trade is a risk reversal where you buy out of the money puts and you sell out of the money calls. The risk reversal has a low vega and a low delta, hence you have an almost pure skew exposure. Alternatively, you could buy a call spread or sell a put spread, but then you pick up some deltas and would have to add a delta hedge. If your view is that the kurtosis or smiliness will increase, then you buy the wings and you sell the center. That is, you sell at-the-money options and you buy low strike and high strike options. The typical trade is a butterfly. But note that with a normal butterfly, you pick up some vega. To turn the structure vega neutral, you buy a bit more of the wing options than you sell at-the-money options. Now you have a pure smile exposure. Finally, let's assume that you have a view on the term structure of volatility. Assume again that we start with a flat structure. So in our graph, the x-axis is the time to expiry and the y-axis the implied Black-Scholes volatility. Say your view is that the term structure will steepen. You can express this by buying calendar spreads. That is, you buy at-the-money options with a longer time to expiry and you sell at-the-money options with a shorter time to expiry. You will have to adjust the number of options such that your overall vega is 0, and you might also add a delta hedge. And this was Module 3. We discussed the basics of volatility, realized volatility, implied volatility, how you trade realized volatility, how you trade implied volatility. In Module 3, we also talked a lot about uncertainty and distributions. We looked at market distributions and we looked at distributions implied in option models. But this will not be a focus on the test.